Hey everyone, this is the third lesson on Abstract Algebra, and today we're going to be talking about homomorphisms and isomorphisms, and of course relevant theorems and results related to those topics. So to understand what goes on with this subject, you have to understand that mathematicians commonly want to compare different things like groups. And so the question is, how do you compare groups? And how do you compare the structure of groups? And how do you know groups have the same or different structure? And so usually in math, what you do is to compare two mathematical objects, you create a map between them. And you see what properties it has. Or if there's a certain kind of map. If you remember maybe from analysis or set theory, there might be a bijective function or a continuous function, and that tells you something about how one space relates to the other. So when we want to find when two groups have the same structure, we're looking for a map between them that has a certain property. Now, the structure of a group, it relates to its multiplication law. And the elements in the group. So we should hope that our definition for what a homomorphism is, which is a map that preserves the structure, has both of these as a part of the definition. So let's go right into it. So we're going to need two different groups because we're comparing them. Let G and dot G, so this is going to be referring to the multiplication law in G, and H and dot H be groups. A homomorphism, which is a very cool word to say, of G and H is a map, let's call it phi, from G to H, such that for all G1, G2, and G, you just satisfy this one rule. Phi of G1 times G2 equals phi of G1 times phi of G2. Okay, great. So to kind of understand what's going on here and how it relates to what we were talking about before, is what we have here is one side is like multiplying in G, and then that relates to multiplying in H. So basically what this map is saying is that there's some similarity to how you multiply in G and how you multiply in H. That similarity is related to this map phi. When you map phi of G1 and phi of G2 and multiplying them together, that's the same as just mapping phi of G1 times G2. So you should really get a good understanding of the fact that the multiplication inside of phi is happening in G, but the multiplication outside of phi is happening in H. These elements are both in H, and these elements are both in G. Okay. So hopefully it should be pretty clear that this, in some way, helps you think about preserving structure of a group. And we're going to prove different facts that's going to make that very clear why this is a great definition. And if you've heard of multiplicative functions before, this is a very similar definition to that. Okay. Another thing mathematicians want to do that we brought up in the first lesson is they want to tell you when groups are the same. So the question is, how do you determine when two things are the same? Now, the word I used in that lesson was an isomorphism. And so an isomorphism should be something like a homomorphism, but we need something even more that tells us more about the sets of the groups, the actual group elements, rather than just the multiplication law. If you remember from analysis or set theory, that thing that told us when two sets were the same was a bijection. So we're going to try to use that again here in group theory. So let G and H be groups from before. An isomorphism is a bijective homomorphism. Homomorphism psi from G to H. So the only thing that's more special about isomorphism is that it's bijective. And if you're unclear what that means, it means it's injective and surjective. Surjective means basically it covers the entirety of the range, which is H here. Injective means if you have psi of x equals psi of y, then x equals y. If you're unclear about those definitions, I recommend searching them up to be more clear before you continue with this video, because we're going to use them in a lot of our proofs. And I should note that there's going to be a lot of different kinds of proofs in this video. It's going to really start getting into good practice with proving stuff in group theory and abstract algebra. So it might be a good idea to pause when we're doing proofs and try to figure out yourself before you see me do it. And they'll have some examples at the end that will give you good practice. Okay, so let's just consider a quick example. I'm not going to go too into depth with this. But if you remember in the first video, I talked about two elements in S3. Well, first of all, we're going to try to prove that D3 is isomorphic to S3. And I took two elements in S3. One was sigma, which basically sent I to I plus 1 and sent sigma of 3 to 1. And so this is kind of like in cycle notation, if you've seen this before, it's equivalent to this, where 1 goes to 2, 2 goes to 3, and 3 goes to 1. Then I also defined a tau, which basically sends 2 to 1, it sends 1 to 2, and it sends 3 to 3. And so hopefully this should kind of remind you of the rotation and flip operators or symmetry operators in D3. In fact, I'm going to define a psi which sends R to sigma and S to tau. And the final rule is that G times H equals psi of G times psi of H for all G and H in D3. And so this is kind of a rule I'm imposing on the function. Now, if you're curious if this function is well defined, you can check that for yourself, but I assure you it is. And so I'm basically imposing the homomorphism restriction on this function, which means to prove psi is an isomorphism, we only need to prove it's bijective. And even more than that, we know from lesson 1 that the size of D3 is the same as size of S3, which means if you remember maybe from linear algebra or something, we only need prove that psi is either injective or surjective, and we immediately get the other one. Luckily, surjectivity is pretty easy because we discussed, or at least I asked you to try to prove, that sigma and tau generate S3. So the quick reason why sigma and tau generate S3 is because I can get 1 tau sigma, sigma squared, sigma tau, and tau sigma. And all these are different elements, and there's 6 of them, so I must generate all of S3. What this means is if I want to get sigma squared, I can just take psi of r squared, which equals sigma squared. And so I can basically generate any of these elements by taking some combination of psi of r and s, and I get another element. For example, this one will send to sigma tau. So clearly, psi is surjective. But like we said, that's enough to imply it's bijective in this case. So thus, psi is an isomorphism. Okay. Now let's try to prove some more valuable properties about homomorphisms in general for abstract groups that hopefully will give you an idea of why homomorphism is a good definition for something that preserves structure. So let phi be a homomorphism from G to H. Homomorphism. And we're going to try to prove the following 4 properties. First one, also note that I'm going to say the identity in G is 1 dot G, and the identity in H is 1 sub H. First property is that homomorphisms send identities to identities. So if an identity in G, you apply phi to it, it sends to the identity in H, regardless of what the homomorphism is. This must always happen. Second one is that for all G and G, you get phi of G inverse equals phi of G all inverse. This one then helps us prove that for all G and G and natural numbers, or should I say integers, because you can do negatives as well, you get phi of G to the n equals phi of G all to the n. And finally, we're going to prove that the order of G equals the order of phi of G for all G and G. Okay. Hopefully, once we prove these, you should pretty much believe that homomorphism is a very helpful definition. Okay. First one. Let's let G and G, and we're going to try to abuse the fact of how identities work on either side, on G and on H. So we can write phi of G a couple different ways. Phi of G can write as phi of G times 1 dot H. Okay, that's pretty clear because that's just how the identity in H works. But you can also write it as phi of G times 1G, because that's how the identity in G works. But by the homomorphism law, I can rewrite this as phi of G times 1G. So these two things are equal, the top and the bottom here. So I can cancel out the phi of G by multiplying by phi of G inverse, because inverses exist, and I get, oh sorry, I should write this as phi of 1G. I get that phi of 1G equals 1H. And note, I assume nothing in particular about this homomorphism. It's completely general about any homomorphism from G to H. It must always send the identity of G to the identity in H. Okay. Little square for that. 2. For all G and G, we want to show that phi of G inverse equals phi of G all inverse. So the definition, let's just let H equal phi of G for now in H. We want to prove that we know there exists an H inverse in H just by the definition of group. H times H inverse equals 1H. And we know that it's unique. So we just need to prove that the example we've given here, phi of G inverse, works. So we just want to prove that phi of G times phi of G inverse equals 1.H. Well, if we apply the reverse of the homomorphism law, what we see is we can bring these two elements inside of phi. And G times G inverse is phi of 1 sub G, which equals 1 sub H. And remember that this came directly from the property we just proved above. So thus, we get that this gets us 1H. So we know phi of G inverse has to be phi of G inverse. Great. This should be another clue that when we have these inverse properties that are being maintained, this is a great definition to have for a homomorphism of groups. Okay. The next one is we want to show for all G and G, n is an integer, phi of G to the n equals phi of G all to the n. Hopefully this should be clear, but we're going to break it up into a couple cases. First is n greater than 0. In this case, we get phi of g to the n equals phi of g times g all n times. And I can then split it up into like this using the homomorphism law. Oops, phi of g, sorry for that. And this occurs n times, which just means you can rewrite it as phi of g to the n. Now let's take n less than 0. We get phi of g to the n. You can rewrite as phi of g to the negative 1 times g inverse times g inverse, and this happens absolute value of n times. So then I can rewrite this as phi of g inverse to the absolute value of n, because it repeats absolute value of n times. But from property above, we know that this is then equal to phi of g to the negative 1 all to the absolute value of n by exponent rules. This is just phi of g to the negative absolute value of n. But if n is negative, then negative absolute value of n is just phi of g to the n. For example, n is negative 3. Negative absolute value of negative 3 is negative 3. And of course, if n equals 0, we just say g to the 0 is 1, and we already know that phi of 1g equals 1h by property 1. That covers all of our cases there. Okay, last property. We want to prove that the order of g equals the order of phi of g. So recall that, let's just first let n equal the order of g and m equal the order of phi of g for some g in g, just like let g in g. Okay. Recall that n is the smallest positive integer such that g to the n equals 1g, and m is the smallest positive integer such that phi of g to the m equals 1h. So we're going to do a proof by contradiction. Without loss of generality, let's assume that n is less than m. If you assume m is less than n, the argument is basically the exact same. So what we get is that we can take, we know phi of 1g equals phi of g to the n, which also equals, as we proved above, phi of g all to the n. But we know that 1g gets into 1h. But we know that n is less than m, so phi of g to the n can't be 1, because then the order of phi of g would be n, but we know n is less than m. Sorry, that makes it look like it's less than or equal. Let me erase that. But we know that this is not equal to 1 sub h, which is a contradiction, because we have this side 1h and this side not 1h, which is a contradiction. Thus, n equals m, as desired. Of course, technically you should do the case when m is less than n, but it follows the exact same process. Okay, great. So now we're going to get into some more definitions that will give us even more theorems and interesting things to discuss about homomorphisms and isomorphisms. So the kernel and image of a homomorphism are defined below. Homomorphism. First is that the kernel of phi, where phi is the homomorphism, and let's say phi is going from g to h, are all those elements G and G such that phi of G equals 1 sub H. If you remember from linear algebra, the kernel was defined as all those elements that get sent to 0. In this case, we can think of the identity as our 0. So it's all the things that get sent to the identity. The image of phi is all those elements H and H such that there exists a G and G where phi of G equals H. You can think of this as all those values in H where phi gets sent to. If you look in the image, there's something in G such that phi of G is that thing in the image. Okay. There's a bunch of interesting things you can prove about the kernel and the image of a homomorphism. We're just going to go over a couple of them. The first thing, which I'm going to call the kernel and image subgroup theorem. Kernel and image subgroup theorem is as follows. Let phi be a homomorphism from G to H. Then kernel of phi is a subgroup of G, and image of phi is a subgroup of H. Sorry, I should have said G here. Kernel of phi is a subgroup of G, and image of phi is a subgroup of H. So let's try to prove this. And now, I don't know if I referenced this in the last episode when I talked about subgroups, but we have to prove that something is a subgroup is that it has inverses, closed under multiplication, and it has the identity. The reason why we have to have the identity is because we don't want our definition for a subgroup to include something that has nothing inside of it. That would be a lame definition. It always has to have something. In fact, it always has to have the identity because it needs to be a group itself. Okay. So we're going to start with the kernel of phi. So let G1, G2 be two elements in the kernel of phi. We're going to try to prove that G1, G2 is also in phi. And consider H equals G1 times G2. We want to prove that phi of H equals 1H, because that implies that H is in the kernel of phi. Well, phi of H equals phi of G1 times G2. By the homomorphism law, this is phi of G1 times phi of G2. But since G1 and G2 are in the kernel, this is 1H times 1H, because both of them get mapped to the identity, which is just 1H. So thus phi of H is 1H, so H is in the kernel of phi. Okay. Now let's prove that there are inverses. So let's let G in the kernel of phi and consider the fact we want to prove that phi of G inverse is 1H. Okay? Well, we know that phi of G inverse equals phi of G all inverse. But phi of G we know to be 1H because G is in the kernel of phi. And 1H inverse is just 1H. And this is pretty obvious from above. If you multiply 1H by itself, you get the same thing back. 1H. Thus, G inverse must also be in the kernel of phi. The final thing we need to prove is that the identity is in the kernel, but we already know this. Remember one of the properties we proved, that's phi of 1G is 1H. Thus, 1G is in the kernel of phi. So kernel of phi is a subgroup of G. Okay, now let's look at image of phi. Let H1, H2 in image of phi. Then I want to consider those G1 G2 in G such that phi of G1 equals H1 and phi of G2 equals H2. So we want to prove that H1 times H2 is in the image. Okay, well, we notice that if we take phi of G1 times G2, which is in G, this equals phi of G1 times phi of G2 equals H1 times H2. But if you notice, this is exactly what we mean by H1, H2 being in the image. There exists something in G, G1 times G2 to be clear, such that phi of G equals H1 times H2. Thus, H1 times H2 is in the image. Okay. Now let H and H, and we're going to let G and G such that phi of G equals H. We know from one of our properties that phi of G inverse equals phi, you see this one's very helpful, phi of G all inverse, but phi of G is H, so this is H inverse. Since G inverse is in G, clearly H inverse must be in the image of phi as well. Finally, we need to prove that it has the identity. Once again, is that first property we proved, which is phi of 1G equals 1H. So 1H must be in the image. And thus, image of phi is also a subgroup of H. Okay. So hopefully this should give you the idea that when you're looking at homomorphisms, these two objects, the image and the kernel, are very important things to look at to identify what happens with this homomorphism. We see they both form subgroups in their respective fields, or groups I should say, the kernel in G and the image in H. We're going to learn one more thing that we can use to characterize homomorphisms. And this is a theorem. And it's called, I'm going to call it the injective homomorphism theorem. Homomorphism theorem. It says if phi from G to H is a homomorphism, then phi is injective if and only if, that's what I mean by the if and only if, the kernel of phi is just 1 sub G, is the trivial group, is the thing that's only the identity. So this is pretty powerful because, well, if we look at the proof, doing it one way is very easy, which is to say, doing it this way, first assuming that phi is injective, is actually very easy. So assume phi injective. Well, we know that phi of 1G equals 1H, which means we already have something that equals 1H. But that means that nothing else can get sent to 1H. For example, if there exists, let's say, G and G such that phi of G equals 1H, well then phi of G equals phi of 1G. And since phi is injective, that would imply that G equals 1G. So we just get that 1G is the only thing in the kernel. Okay. So that's that direction. Now let's do the other direction, which somehow seems way more powerful. So assume that the kernel of phi equals just 1G. First, I want to see if you should take a second and try to prove this on your own. If you can't, just continue watching, and we're going to go over the proof together. Okay. So what we're going to do is take G and H and G and assume that phi of G equals phi of H. We're going to try to prove that G equals H, which is the same thing as proving that phi is injective. If phi of G equals phi of H, I'm going to multiply both sides by phi of H inverse. H. Then I'm going to rewrite this as phi of G times phi of H inverse using the property we learned, which is the same as, by the homomorphism law, moving it inside, phi of G times H inverse, which means G times H inverse is in the kernel of phi. Since if you map it, phi of G times H inverse is 1H. But what that means is we know the kernel of phi is only 1G. Finally, that implies if we multiply both sides by H, we get G equals H, exactly as we wanted. Thus, phi was injective all along. So this is an extremely helpful theorem for proving when homomorphisms are injective or not. And also very helpful if you're trying to prove there's an isomorphism between two groups. Because, let's say like for D3 and S3, we know they have the same size. So being injective is the same as bijective. So if we can easily prove injective by taking our map, finding the kernel of it, then it's very easy to prove if a homomorphism is also a bijection or an isomorphism in certain cases. And I don't know if I mentioned this before, but if there's a homomorphism between two maps, or two groups, then those groups are homomorphic. And if there's a isomorphism between two groups, those two groups are isomorphic. Okay. Now we're going to prove some other theorems about isomorphic groups that are very helpful. Okay. So let G and H be isomorphic. We get G is abelian if and only if H is abelian. We also get G is cyclic if and only if H is cyclic. If you're curious what cyclic means, I'm going to define it in a second and leave it as an exercise for you to do. Okay, proof. Let G be abelian. Now let psi from G to H be an isomorphism. Let H1 and H2 and H. Since we know G is abelian and we want to prove H is abelian, we're going to take two elements in H and show that they commute with each other. So we're going to take these two elements and we're going to consider the following diagram where we have that psi of G1 equals H1 and psi of G2 equals H2. We know that these G1 and G2 must exist because psi is an isomorphism. So there has to be something that gets into H1 and something that gets into H2 because it's bijective. Consider the following diagram. This is psi of G1 times psi of G2, which is H1 times H2. But this is also psi of G2 times G1 because G is abelian, so I can change around the order of G1 and G2 and this is h2 times h1, and thus we get that these are equal. So h1 and h2 commute. Thus h is abelian. A similar argument can be used if you assume h is abelian and you want to prove g is abelian by doing the same trick where you switch around h2 and h1 and it switches around the things in here. Since psi is injective, you have to know that g1 times g2 equals g2 times g1. Now, for the other thing, which is proving cyclic groups are the same when they're isomorphic, is I need to define what cyclic is for you. So a cyclic group, a group is cyclic if there exists G in G such that G equals 1 comma G squared all the way to G to the n minus 1, where n equals the order of G. What this means is I can keep on multiplying elements of G until I generate the entire group. This is also the same as saying that the order of G equals absolute value of G equals n. So this is the definition of a cyclic group. If you're curious, Z mod n is an example of a cyclic group. And so you want to try to prove that if a G is cyclic and G is isomorphic to H, then H is cyclic, and the other way around. So that's a good example for you to try on your own. Okay. One more definition. This is for a very specific kind of isomorphism. In automorphism, of a group G is an isomorphism psi from G to itself. That's where the word auto comes from. It just goes from G to G. So definition's pretty simple. But the examples are very interesting. So, for example, let's fix some element G in G and define a mapping psi sub G of H equals G times H times G inverse for all H and G. This mapping has a very specific name. It's called the conjugate mapping or conjugation by G. So we want to prove that this is an automorphism, which means we need to prove it's a homomorphism and it's bijective, because we know it goes from G to G. So let's first prove that it's a homomorphism. So let's say we have H1 and H2 in G, and we look at psi sub G of H1 times H2. Well, that equals G H1 times H2 times G inverse. But I can separate this very cleverly into G H1 G inverse times G H2 G inverse. And if you see what happens, these middle two terms will cancel out and get us the same thing. But this is equal to psi sub G of H1 times psi sub G of H2. And this is the exact homomorphism law that we need. Okay, so psi sub G is a homomorphism. And now, to prove it's bijective, since it's just going from G to itself, we need only prove it's either injective or surjective. But if you remember, we proved a very nice theorem about how to prove a homomorphism is injective. So let's try to do that. We want to prove that psi sub G is injective. The theorem told us that this is equivalent to proving that the kernel of psi sub g equals just 1 in G. Okay, so that means let's just take something in the kernel and we're going to prove that this thing has to be 1. This means that psi sub g of h equals 1. But psi sub g of h is also GHG inverse. Thus, GHG inverse equals 1. So GH equals G. But if we left multiply by G inverse on both sides, we just get that H equals 1 as desired. So if H is in the kernel, H has to be 1. Thus, the kernel of psi sub G equals 1 as we desired, which means psi has to be injective and thus bijective, and thus psi is an automorphism. And this is true for all G and G. The map which does the conjugation by G is an automorphism regardless of which G you choose. Okay, that's great. I'm going to end off on some examples that I think you should try on your own, because the proofs have really ramped up in this lesson, and so it should be really good practice if you try to do some of these slightly harder proof examples. Also good for a review. Okay, first one. Let psi from G to H be an isomorphism. Prove psi inverse is also an isomorphism. Just say iso. So this is like saying the map psi inverse, which goes from H to G, is also an isomorphism. We know if G and H are isomorphic, it should be pretty clear that there should be a way to go from H to G, and psi inverse is a great way of doing that. Okay, example 2 is prove that G is abelian for some group G if and only if the automorphism we just defined, psi sub G from G to G, is the identity map for all G and G. So this means that whatever G you decide to fix for psi sub G of H equals H for all H and G and G and G is another way of writing this. Whatever G and H you choose, psi sub G of H is going to be equal to H. Okay. Then the third exercise, which might be the hardest, is we're going to find a new set, which is called the aut of G, which is going to be the set of all the automorphisms of G. So this is all those maps psi from G to G, such that psi is an automorphism. Auto. Prove that the group, or that I should say the set, aut of G with the composition operator is a group. So prove that the set of automorphisms of G with the composition operator, which means composing two functions, forms a group under this operation. This is super interesting and has a lot of applications in Galois theory if you ever want to study it, when you have to study things like the Galois group, and that rests upon this fact that the set of automorphisms forms a group under its composition of functions. Okay, if you can prove all three of these examples, I think you're doing just great in learning abstract algebra so far, especially this third one. So these are not easy at all. So thank you for listening. I hope this was helpful.